Hi, this is the third video from the series of examples on DC motor analysis. So if you haven't watched the first video, please find example 1. It's on the no load speed of the DC motor. Example 2 will carry on to look at the speed of the DC motor at a certain current condition. And in this video, example 3, we will look at how to calculate the torque and efficiency of a DC motor for a given line current. So let's proceed with the video. Now we're moving on to the third example, and this third example we have a DC motor, which is a separately excited DC motor. There's compensating windings, so there's no armature reaction, and this time we're going to calculate the torque and efficiency of the motor for a certain condition. So when we do DC motor analysis, normally what we want to calculate is the speed, the torque, and the efficiency. So what we're going to do, we're going to continue for the same machine as in example 1 and example 2, where we had these parameters of the DC motor. But the extra information that we need to calculate torque and efficiency is the core loss, which is given here as 750 watts, and the loss due to friction and windage, which is 450 watts. So what we're going to do, we're going to calculate the induced torque and the efficiency of the DC motor with our adjustable set at 200 ohms and a line current of 90 amps. So this is exactly the same condition as in example 2. But in example 2, we calculated the speed. It came out to be 203.39 radians per second. Now we're going to calculate the torque and the efficiency at this condition. So the information given is the core loss power is 750 watts and the friction and windage loss is 450 watts. So if we go back to example 2, when the R adjustable was set at 200 ohms, the field current was 0.6 ampere, and when the line current is 90 amperes, the armature current is equal to the line current, which is 90 ampere, because it is a separately excited DC motor. And we found that with this armature current of 90 amperes, the EA was 132 volts. We got this from the KVL of the armature circuit. And the speed was 203.39 radians per second. So we need this value of armature current, EA, and the speed of 203.39 radians per second. We're going to use this to calculate the induced torque and the efficiency of the motor to answer this example. Now, in order to solve for induced torque and efficiency, we need to look at the power flow diagram of the DC machine, in particular the DC motor. So as we've seen before, the power flow shows the relationship from input power right up to output. So in order to calculate input power, the equation is Vt times IL. Then we need to minus the electrical losses. For separately excited, the electrical losses is from the armature resistance. So it's IA squared RA. For the shunt DC motor, we have two sources of electrical losses, which is the armature resistance IA squared RA and the resistance in the field winding RF plus R adjustable multiplied by IF squared. After we deduct the electrical losses, then we'll get the converted power. So converted power is input power minus the electrical losses. Another way to calculate converted power is EA times IA. and this will equal induced torque times omega m. So converted power is the power converted from electrical to mechanical form. So everything after this line is mechanical power. Now on the mechanical power side, the losses are core losses, which is from the hysteresis loss. Okay, remember the core is made of ferromagnetic material, and as we've learned before, ferromagnetic material has a BH curve. So the BH curve causes hysteresis loss. Okay, then after core loss, there is friction and windage loss and stray losses. Friction and windage loss is due to the air gap and the friction at the air gap, and stray losses are other losses which can't be explained. So after we've deducted all these losses, then only we will get the output power, which is in mechanical form. The output power is your converted power minus all the losses that we've seen just now. So it's the converted power minus your core loss, friction and windage loss, and miscellaneous or stray losses. And another way to calculate converted power is the load torque times omega m. Now, the load torque is not equal to induced torque due to the core losses, the friction and windage loss, and the miscellaneous loss. Okay, and sometimes these three losses can be lumped together and called rotational losses, or sometimes called mechanical losses. Okay, so all three of this, sometimes we call this P rotational or P mechanical loss. So now let's get back to our example. So now we're back to our example. We're going to calculate when R adjustable is 200 ohms, the induced torque and the efficiency of the DC motor when the line current is 90 amperes. So from example 2, when R adjustable is 200 ohms and IL is 90 amperes, we found that IA will equal IL, which is 90 amperes. Again, this is a separately excited, so that's why it's the same. And at this condition, EA was found to be 132 volts with a speed omega of 230.39 radians per second. So to calculate induced torque, if you refer back to the power flow diagram, induced torque is related to converted power, P converted, which is given by the equation P converted equal to EAIA, and is also equal to T induced times the speed omega m. So therefore, from this equation, T induced is EA times IA divided by the speed. And this speed must be in units of radians per second. So if we put in the values, EA is 132, IA is 90, and the speed is 230.39 radians per second. So this gives us an induced torque of 58.42 Newton meters. So this is the induced torque when R adjustable is 200 ohms and IL is 90 amperes. So I repeat, to get induced torque, the equation is EAIA divided by omega m, and the speed must be in radians per second. We now move on to calculate the efficiency. Now, efficiency is given by the output power over the input power and multiply 100% to get it in a percentage. So in order to calculate efficiency, we must look at the power flow diagram and look at how to calculate the input power, P in. From the power flow diagram, input power is the input to the armature circuit, which is Vt, times the current that is given to the armature circuit, which is IL. And we know for this question, Vt is 150, IL is 90, so therefore P in is 13500 or 13.5 kilowatts. So to get next the output power, if you look at your notes, from the power flow diagram, P out is your converted power minus the core losses minus the friction and windage loss and minus any stray or miscellaneous losses. So before we can calculate P out, we need to get the converted power. And from the equation previously, P converted can be calculated from EA times IA. So in this condition of 200 ohms R adjustable and 90 amps line current, EA was 132 volts and IA was 90 amperes. So this gives our converted power to be 11,880 watts. Another way to calculate converted power is from the equation P converted is equal to P in minus P electrical, where P electrical is what we call the electrical losses. Okay, and for the separately excited DC machine, P electrical is only at the armature side, which is related to RA. RA is the source of the electrical losses. So the current through RA is IA, so the electrical loss is IA squared times RA. IA is 90 squared and RA is 0.2. So the electrical loss is 1620 watts. So therefore, P converted, P in is 13,500 minus P electrical 1620, and this comes out to be 11,880 watts, which is exactly the same as what we had calculated earlier. So there's two ways to calculate P converted, using EA times IA or using P in minus P electrical. Just be aware that for electrical losses, if it's separately excited, you only need to consider RA, but if it's a shunt DC motor, then you also need to consider the losses in the field winding due to RF and R adjustable. Now that we have calculated the input power to be 13.5 kilowatts, converted power was 11,880 watts. We now can go on to find the output power, which is P converted minus the core loss, minus the friction and windage loss, and minus any stray or miscellaneous losses. So from the question, it was given that the core loss is 750 watts. So it's given that P core is 750 watts and the friction and windage loss or the losses due to friction and windage, is 450 watts. There's no mention on the stray losses, so we can assume the stray and miscellaneous losses is 0. So therefore, P out is P converted minus the core loss minus the friction and windage loss. So 11880 minus 750 for core loss and 450 for friction and windage loss. So that gives us an output power of 10,680 watts. So finally, we can calculate the efficiency. The efficiency is P out over P in times 100%. So P out was 10,680 watts, P in was 13,500 watts, and we get this in a percentage form. That comes out to be 79.11%. So this is the efficiency when the DC motor has an adjustable resistance set at 200 ohms and a line current of 90 amperes. Now, if the question was extended and they ask you to calculate the output torque, then the output torque or load torque is P out divided by omega, or the speed of the machine. So you can get it from 10,680 divided by 230.39, which is the speed in radians per second, and gives this you an output or load torque of 46. So P out over the speed gives you a load torque or output torque of 46.36 Newton meters. Now, comparing this to the induced torque was 58.42 Newton meters. And you'll find that the induced torque should always be bigger than the load torque or output torque, because you need to overcome the losses in the core and the friction and windage and the stray losses, if any. So that's why the induced torque is always larger than the load torque.